Wow. Okay. Introduction to the lab. The purpose of this lab is to figure out how much energy you'd have to put a glider into space. Pretty simple. What do I mean by space? So space is actually kind of fuzzy. There's no real definition on where space starts. But for my purposes, I was going to use the Kármán line, which is 100 kilometers above the Earth's surface, or 100,000 meters. So some of the fundamental principles at use here are the energy principle, Newton's second law, and all of our formulas that come out of that, our position update and our velocity update formula. VF equals VI plus AT, and then RF equals RI plus VT, where T is like the time change. And the forces, we are going to assume the forces are non-constant, because they are in this instance. So the lab setup, the physical part of the lab was just this glider I built. Technically, I mean, to be fair, I built this glider for AE 1601, but I was like, you know what, this is actually kind of cool. Let me repurpose this into a glider for this class. So I did. And then, unfortunately, upon testing, I immediately broke it. Yeah, the first test flight I did to try to get some data, it went nose up. I threw it poorly, it went nose up, and it came down on its tail and broke the tail off. So it's broken on my floor right now. So we're not going to actually get any good lab, good physical videos. So sorry about that. So this is going to have to be an entirely computational model. Some of the values for the computational model I did get from the glider itself, so I guess it was helpful for that to that extent. But here's the setup. We have, our initial conditions. The glider is about 100 grams or 0.1 kilograms. The system is just the glider, and the surroundings are the the force you put into it with your the energy you put into it with your hand, the force, the work due to lift, work to drag, and work due to gravity. Here are the calculations. So the calculation step is kind of interesting, because lift affects the y direction only, but is derived from speed in the x direction. So here you can see my formulas for it. Unfortunately, my glow script was just freezing. Like, as soon as I would hit run, it just immediately froze, and the entire browser would freeze, and I kept having to restart the browser. So the third try, I gave up. And there's the equations. Those would work. If you ran it, it would simulate a loop where it would test an increasing number of velocities to see how fast the glider would need to go in order to get high enough before, because drag. So when we drag in the model, drag slows it down. It needs speed to have lift, so it would test an increasing velocity until it found one where it would get to 100,000 meters before the drag slowed it down to the point where it stalled out and fell back to the earth. Unfortunately, the math on that is, so there's my rough math on just the energy equation to take, where V is an unknown variable. Unfortunately, because drag is a pretty complicated thing, and so is lift, I both had to simplify a lot in the model, and because the model won't run, because I cannot get GlowScript to run, neither works. So I can't actually figure out what the velocity is, because I have to do it. My algebra is not good enough to figure out how to do that algebraically, so I was going to have to do it just iteratively and calculate it that way. And I have no idea how to do that. So you're going to have to stick with, these are what the graphs would look like. I've thought about it for a little bit. The b squared term on drag is going to increase a little bit faster than the v squared term, or the v squared term on drag has a greater coefficient than the v squared term of lift, so it's going to increase a little bit quicker. So that's how you're going to get that tailed off kind of shape there. And there's my math on the forces and the work. What does it mean? So what affects the amount of energy required to get something in the air? It's actually really complicated, way more complicated than I thought when I started. But the main thing is, it really comes down to just drag coefficient versus lift coefficient. Whether or not, which grows faster. In this case, in my glider's case, so it needs to be improved. The drag grows faster, so you need a lot of velocity before it slows down too much. Before it slows down enough that where it won't produce any lift. But in a more efficient glider, you would need less velocity and less energy. That's really the real thing. You could figure out. The real thing about this lab is you could figure out how efficient to make a glider to make it not, or make it require less energy to get higher up in the air. Oh, another important thing to mention is that I've simplified drag and lift a lot, like a lot, because they're both very complicated things that I don't know how to do until my third year here. And also, I ignored changing air pressure relative to altitude because at